This is the first lecture video for Chapter 17, Free Energy and Thermodynamics. We want to begin our discussion first by looking at the first law of thermodynamics. And basically it says that you can't win. The first law of thermodynamics states that energy cannot be created or destroyed. The total energy of the universe cannot change, but you can transfer it from one place to another. So we write that mathematically as an equation. So the change in energy of the universe, remember change is final minus initial, is always going to be zero. The energy change of the universe is going to be equal to the change in energy of the system that you're looking at and the change in energy of the surroundings. So you can move that energy around from the system to the surroundings and vice versa, but the total energy of the universe cannot change. Sometimes we call the first law of thermodynamics the conservation of energy. And for an exothermic reaction, lost heat from the system goes into the surroundings. And there are two ways energy is lost from a system. It can be converted to heat, and remember heat equals Q, or it can be used to do work, which is W. And you'll probably see a lot of review information from your Chem 1A course. Energy conservation requires that the energy change in the system equal the heat released plus the work done. So the change in energy of the system equals Q plus W. So you should have seen this in your Chem 1A course. And we can write also that the change in energy, where Q is the change in enthalpy plus P times delta V, where we can express the work as pressure times the change in volume. And remember, the change in energy is a state function. So the internal energy change is independent of how the energy change was done. So it doesn't matter how it happened, how it got there. We're just looking at the total change in energy of the system. Now, one of the analogies of looking at energy changes as a system is there's an energy tax associated with things, and basically you can't break even. So to recharge a battery with 100 kilojoules of useful energy will require more than 100 kilojoules of energy. And every energy transition results in a loss of energy, basically because there's some conversion of energy to heat, which is lost by heating up the surroundings. So we're going to look at two different systems for heating. There's heating with natural gas. So basically you burn the natural gas and you get your heat. But there is some heat lost to the rest of the surroundings that you don't get to feel. So you get to feel some of the heat from the burning natural gas, but some of it's lost to this escaping system. So let's look at heating with electricity. So we start with burning fossil fuel. So you're releasing heat as you burn the fossil fuel, and this makes steam, and the steam turns the turbine, which generates electricity, and the electricity has to then travel through the wires, so you have to transport the electricity somehow. And then once the energy comes into your house, then it has to go through another process as it's converted into the heat when you plug in your electric heater. So there are lots of different steps along the way to get to the heat, but each time you had this conversion of energy, you lost some of the heat, or you lost some of the energy along the way. So we call this the heat tax, or the tax on the energy. Now generally fewer steps result in a lower total heat tax. Now we want to talk about thermodynamics and spontaneity. Thermodynamics predicts whether a process will proceed under the given conditions. So basically, is the reaction spontaneous or not? Will it happen on its own? And a non-spontaneous process requires energy to be put into the system. So spontaneous just happens on its own, but a non-spontaneous, you've got to do something to make that reaction happen. The spontaneity is determined by comparing the free energy of the system before the reaction with the free energy of the system after the reaction. If the system after reaction has less free energy than before the reaction is thermodynamically favorable. And this free energy is the energy that's actually available to us after we've lost our energy tax. So think about, you're getting your paycheck and you talk to your boss, oh, this is how much you're going to make. And then once you get your paycheck and you're like, wait a minute, I thought you said I was going to be making, X amount of dollars, and this is a lot less than what you said I was going to be making. Well, the government has to take its taxes out, and so you have the amount of money that you actually bring home, so your net versus your gross. So the same thing happens with energy. And the free energy is the amount that you actually get to use. So that's kind of like your net take-home pay. But the total energy is what they promise that they're going to pay you. But you don't get to use all that because the taxes are taken out. Another analogy to look at free energy and describing what free energy is. Let's say you're going to start your own cupcake business and you figured out how much it costs to buy your flour, your sugar, all your ingredients, and you've priced out how much you can sell the cupcakes for. And when you sell your cupcakes, you expect a certain amount of profit. But in reality, you're probably going to be making less than what you expected based on your calculations for your profits, because something usually happens along the way. Usually you may spill some of your flour. Somebody may be eating a couple of your cupcakes, who's working for you, but usually you don't get to make all of your money. Some of it gets lost along the way through different pathways. It's kind of the same thing with energy transfers. Some of it gets lost along the way, and we call this the heat tax or the energy tax. And you only get this net available amount of energy. And this net available amount of energy is what we're terming the free energy of the system. Now, when we're talking about spontaneity of a process, spontaneity has no indication of whether or not the reaction is fast or slow. So something could be spontaneous, such as, explosion with dynamite. So if you initiate the reaction and the dynamite explodes, that's a spontaneous reaction and it happens very quickly. But other processes can occur, but it could occur so slowly you don't even notice a change. For example, how the saying is that diamonds last forever. Diamonds really don't last forever. They slowly decompose into graphite, but it's such a slow process that our eyes don't detect it. Now, the direction of spontaneity can be determined by comparing the potential energy of the system at the start and at the end. So notice in this picture here where this guy is pulling up this block using this pulley system. So the block starts off at the ground, and as he pulls the block up, the block has more and more potential energy. And then once he gets the block pulled up to a certain level, and if he lets go, then it releases all that energy. Now, another example of potential energy, there's chemical potential energy. So we have sodium chloride, so solid sodium chloride, and when you put it in water, it will spontaneously dissolve, so it'll mix and the ions will dissociate into the water. So in the form of the salt, or the solid sodium chloride, there's some chemical potential energy there because everything's all nice and neatly ordered. But when you put it into the water and it spontaneously dissolves, there's a release of energy as it dissolves. So the direction of spontaneous change is going from the solid to the aqueous phase. And like the pulley system, the direction of spontaneous change was going from the lifted state and to where he drops it and it falls to the ground. Now, any spontaneous process is irreversible. It only happens in one direction. But a reversible process will proceed back and forth between the two end conditions, and this is what we term equilibrium. And this basically results in no change in the free energy. So in the previous chapters, we've covered a lot of different equilibrium systems where it transfers from one side of the reaction and back and forth. But there are some reactions that are one way, that it's spontaneous in one direction, but it's not going to naturally occur in the backwards reaction. For example, our neutralization reactions, we said those were one-way reactions. Those were spontaneous reactions that only occur in one direction, but it does not go in the reverse. But our equilibrium system, so with the weak acids dissociating, for example, that would be a reversible process. Here we see another irreversible process. So we start off with a car, you let it expose to the environment, and eventually it starts to rust. And so that rusting process is a spontaneous process. But getting back to the nice, pretty, new looking car, that's a non-spontaneous process. You basically have to put in some energy and you have to put in some work to get the car looking back to its original condition. If a process is spontaneous in one direction, it must be non-spontaneous in the opposite direction. So the rusting of the car is a spontaneous direction, but going back to the pristine state of the car is the non-spontaneous direction. So we want to look at the difference between thermodynamics and kinetics. Thermodynamics deals with the energy changes and looking at the final and the initial system. So thermodynamics, here we're looking at the reactants. Here we're at an initially lower energy, and then as we go to the products we're a little bit higher in energy here in this example case. So thermodynamics looks at the change from the final to the initial and the relative changes there. But as the reaction progresses, there's this higher energy state, there's this intermediate, and this intermediate determines how fast the reaction will go. So if you have a large barrier to get over, then the reaction will be slower. But if you have a small barrier, then the reaction will proceed faster. So the kinetics has to do with the rate of the reaction and how large this active energy of activation is. But thermodynamics just looks at the initial and the final states. Here we're looking at diamonds, and so this is the molecular structure of diamond. Diamond is what we call a network covalent compound. So each of these black spheres represents a carbon atom, because diamond is made completely of carbon, and each of those carbon atoms is tetrahedrally bound. So those all these covalent bonds within the diamond, and this is what gives diamond its unique hardness and strength, because you've got so many covalent bonds. But over time, this diamond will decompose and convert to graphite. And graphite are these sheets of carbon. So it kind of looks like chicken wire if you were to look at it from the top. But you have these layers of graphite, and you have intermolecular forces that interact in between the different layers, but those are very weak. So the layers have a tendency to slide past each other. So this is why graphite is used as a lubricant. But the decomposition of a diamond to graphite is a spontaneous reaction. So it'll happen on its own, but the graphite won't be converted back to a diamond. To convert the graphite to the diamond, you've got to go to very high temperatures and pressures. So you have to put work into it, you have to put energy into it to convert it back into the diamond. So that's a non-spontaneous direction. But the kinetics of this reaction, it's very slow. It takes a very long time for a diamond to decompose to a graphite. And this is because the kinetics of the energy are very slow, because you have a very high energy of activation. Because to convert it from this molecular covalent compound, we've got all these covalent bonds, and you have to break these bonds, and that takes a lot of energy, that energy of activation. The process of going from a diamond to graphite is slow. So let's just look at the reaction for a diamond going to graphite. So initially, let's say our diamond is here on an energy level, but the graphite is lower. So the graphite is more stable, so this is why it's spontaneous going from diamond to graphite. But to get there, there's a very big hill that it has to overcome to get overall lower in energy. And because it takes so much energy to get over that hill due to breaking all the bonds in the diamond, this is why the reaction is slow, even though it's favorable going from the diamond to the graphite. Now I'd like to look at some of the factors affecting whether a reaction is spontaneous or not. There are two factors that determine the thermodynamic favorability, and they are enthalpy and entropy. The enthalpy is a comparison of the bond energy of the reactants to the products. So the bond energy is the amount of energy needed to break a bond, and we express that as delta H, or the change in enthalpy. The entropy factors relate to the randomness or the orderliness of a system, and we represent change in entropy as the delta S, so S represents entropy. And typically the enthalpy factor is more important than the entropy factor. So the delta H typically has a bigger factor than the delta S. So we're going to focus more on the enthalpy, and that's related to the internal energy of the system. And we express enthalpy as the delta H, and generally in units of kilojoules per mole. And the stronger the bonds, the more stable the molecules. If a product is more stable than the reactants, then energy is released. This is an exothermic reaction. And if energy was released and energy is coming out, then the change in energy of the system is negative. If the reactants are less stable than the products, so energy is absorbed, this is an endothermic reaction, and delta H is positive. The enthalpy is favorable for exothermic reactions and unfavorable for endothermic reactions. So since the exothermic energy releases energy and you go to a more stable system, that enthalpy change is favorable. But for endothermic reactions, remember you have to put energy in, so the final state is higher in energy than the initial state, so that is unfavorable. And if you'll recall from Hess's law, that the change in energy of a reaction is going to be equal to the sum of the delta H's for the products minus the change in the delta H's for the reactants. Now entropy is a thermodynamic function that increases as the number of energetically equivalent ways of arranging the components increases. And we said that entropy is abbreviated as S, and generally we're in units of joules per mole. Entropy can be expressed as K times the natural log of W, where K is the Boltzmann constant, which is 1.38 times 10 to the minus 23rd joules per Kelvin. And W is the number of energetically equivalent ways, and this is a unitless number. Random systems require less energy than ordered systems. Here we're going to look at a system where we have energetically equivalent states for the expansion of a gas. So we're saying that there's no energy difference in state A, state B, or state C. So in state A, we have 4 atoms all on one side of the container. State B, with those 4 same atoms, are on the right hand side of the container. And in state C, they're evenly dispersed on both sides of the container. Now the initial arrangements that we showed you were the macrostates. So we're looking at state C here, where we have 2 of the atoms on one side and 2 of the atoms on the other side. This is a macrostate, so all we know is we have 2 atoms on one side and 2 on the other. But there are several different arrangements that can be made from these particles if we were to identify exactly which atom was in which place. So imagine if these were people, and I have two people on one side and 2 people on the other. Well, maybe there's different arrangements. If I name those, I could have Bob and Susan over here, and Sharon and Alan over here, or I could have Sharon and Alan on this side, and Bob and Susan on the other side, or Susan and Sharon on one side. So there's lots of different arrangements that we can put these if we individually label each atom. So the macrostates are where we don't know the names of the atoms or the people. So the macrostate is just knowing that I have 2 on one side and 2 on the other. The microstates are when we know exactly which one is in which spot, when we individually identify each of those atoms. So looking at macrostate, where we had 2 on each side, there are 6 different possible arrangements that result in the same macrostate. So here we've named our atoms 1 and 2 and 3 and 4. Very original names, I know. So all of these microstates have the same macrostates. So they have the same overall energy. They're just different ways that we can arrange them. So 1 and 2 and 3 and 4, or 2 and 3 and 1 and 4, 2 and 4 and 1 and 3. So these 6 different arrangements are the 6 possible ways that these 4 atoms can be placed in the system. So each one of these individual pictures is a microstate, but the macrostate is where we don't have any labels on them and we don't know exactly which number of atom that is in there. So now we're going to go back and look at the macrostates. And we said we're looking at 3 possible macrostates. Now in state A and B, there's only one possible arrangement that I can have. So in state A, if all 4 are on the left-hand side, there's only one way I can do this because I only have 4 atoms. And in state B, if I want all of my atoms on the right-hand side, and it's only 4 atoms, there's only one way I can do this. But in state C, we showed that there were 6 different ways that I could arrange the system where I have 2 atoms on one side and 2 atoms on the others. So therefore, state C has a higher entropy than either state A or state B. So a lot of times when people talk about entropy, they'll discuss and they'll say that entropy is the randomness or the disorder of a system. And to an extent that's true. It's a good general first approximation, but in reality the entropy term means something a little bit differently, and it's this arrangement of the different possible states. So the more ways that you can arrange the system and still get the equal amount of energy, that's how we get disorder. Now the macrostate with the highest entropy also has the greatest dispersal of energy. So changes in entropy, so we're looking at delta S's. Entropy change is favorable when the result is a more random system. So the delta S is going to be positive. So it's like your room. No matter, when you just clean it, no matter what happens, it seems to just get messy. You come in and you do stuff and it just gets messy. But to get it nice and neat and orderly, you have to put work in to get it to look nice. Some examples of changes that increase the entropy are, first of all, reactions whose products are in a more disordered state. So a solid is more ordered than a liquid, and a liquid is more ordered than a gas. So as you go from solid to liquid and liquid to gas, the entropy of a system increases. Also, reactions which have a larger number of product molecules than reactant molecules. So that increases the entropy of the system because there are more things on the right hand side of the equation than there are on the left hand side. Also, increasing the temperature increases the entropy. And solids dissociating into ions upon dissolving increases the entropy. So here are just some examples of those increases in entropy. So we said the sodium chloride dissolving is an increase in entropy. So notice how nice and neat and orderly the sodium chloride is. You've got this face-centered cubic packing, and each of the cations and anions are neatly arranged, but once you start putting it in water, the water starts to break up those ionic interactions and it solvates the cations and the anions, and there just seems to be some disorder in the system. So this disorder is that entropy that we're talking about. You go from this neat, orderly system to the dissolved aqueous system, so you have an increase in the entropy. Going from a liquid to a gas, so water vaporizing. So you've got more ways of arranging all of these water molecules as it goes from the liquid to the gas. So this is an increase in the entropy. And as you go from ice to liquid water, so as the ice melts, so ice has this nice repeatable pattern. Everything's nice and orderly and packed. But as you apply heat and the ice melts, then you get all of these changes, and the water molecules can then move and wiggle back and forth, and this increases the entropy of the system. There's less order in the liquid than there is in the solid case.